Guys, so today we have lecture 9. And we're going to start using the table. So please pay attention, and you will see that the figures we did in lecture 8 to show the states of the substance is extremely important, okay? I will add the page numbers later. I did not bring my lecture notes. So here we go. This one, I think I'm going to make it up the first one just to make sure that I can show you exactly what I want. So the first one, we're going to have a piston cylinder assembly. Let's say here, example 1. We have a piston cylinder assembly. So you do this figure. Why is this important? Because this indicates that this is a closed system. So we have to deal with a closed system. And the substance over here is refrigerant 22, which basically this is the gas they put in the air conditioning in your car, okay? Refrigerant R22. All right? You know that initially, so as state 1, the state of the R22 is saturated vapor, and that the initial pressure is 4 bar. Okay, and you're going to go to a state 2, which you don't know what it is, but you know that the pressure is 4 bars and that the temperature is 30 degrees Celsius. Okay, so maybe here to help, I think we did the other day, if this is a piston and there's nothing acting on it, what's going to happen to this system between state 1 and state 2? In here, if you hit this, the piston is going to move up, no? If you cool it, it's going to move down. So what is the consequence of that? Is that the pressure, this is a constant pressure process, no? Okay, so this is not really given to you. This is just from coming, you see at the figure, no? Yeah, maybe they might tell you. So over here, what you need to determine is the work per unit mass done by the piston and the heat per unit mass that will move this piston up or down. Okay, so here, again, this is what we know. So we need to do the figure. This is the most important part. If you do this right, these problems are not difficult. If you don't know how to do this figure, it's impossible. Okay? So last time we were looking at the PV and TV figure. So let me do the PV. Yeah, let me do the PV. We could do the TV, but let's do this one. Yeah, I like to do the other one, but let's do this one. So if you remember this figure, what is the mean of the left-hand side of this cover here? This is saturated liquid. Yeah, from this side up here, this is saturated vapor. Okay? So all right, so what do we know? We know that P1 is equal to 4 bars. So let's say, let's put it over here. Let's say P1 equal to P2 equal to 4. So what do we know? Here we are, then let's say it's this point here. State 1 will be located right here, no? Okay? because what do we know? This is saturated vapor. All right, and if you remember these figures PV, what they have lines of constant temperature that come this way down. All right, remember the other day in class, I told you that, let's see if I find it again. You have this table here. This is these two figures. Oh, we didn't, okay, and we'll look at that later. These are the two figures, TV, lines of constant pressure, PV, lines of constant temperature. And I told you you could bring these to class and all the exams, okay? With the page with units, so you know what does it mean. You see here is liquid, mixture, and here will be gas. So you can bring these figures with you so you don't get lost. All right, so let's come over here. So now, what do we know about state 2? So about state 2, we know that the pressure is 4 bars. All right, so okay, let's see what we can find from the tables. So let's go to the tables. We'll come here. You start looking over here. Let's see, R22, table A7, table A8. So we start there. Table A7, table A8. So this one, they give you here the temperatures. Probably is more convenient to us to go to table 8, which now they give you the pressure, okay? Remember, in order to find a point on the figure, what do you need? You need to know two things, no? All right? So over here, we know the pressure is 4. All right, so if you look at here, what is the temperature, they say? Is minus 6.56. Okay, so that if we go to the figure, will mean what? That this line here of constant pressure is T1 equal to minus 6.56 degrees Celsius. We might not need it. I don't think we're going to need it, okay? But I'm just trying to give on the first problem as much information as I can. All right. Maybe one thing I'm going to add first before moving to the next step. Another thing is that if this is saturated gas, this means that this will be here, V gas, for example, the probability will be V gas. And that is equal to what? So let's see, from the table A8 at P equal 4 bars, Vg is equal to what? 0.0581. Okay, so we're going to write that down. So I'll show you now table A8 at P equal 4 bars. We find that, okay, I'll show you now. T saturation we say was equal to T1 equal to minus 6.56 degrees Celsius, and we find that V1 equal to V sub G equal to 0.0581 cubic meters per kilogram. So when we look at this, all right, basically what I did is just write that information from table 8. We find that T saturation was minus 6.56 and that V1 is equal to 0.0581. Okay, we need more information from here, but we do it again. And this time I'm going to go back and forth, okay? We could give all the information that we need now from table A8, but let's do one step at a time. Now what I'm trying to do is just to find out where is state 2. Okay? All right. So what could be state 2 on this figure? You look at this figure, what could it be? If it's constant pressure, what are the different options? Either you can go here, everything becomes gas, correct? Or you could move backwards, you go to this area here where this will be a mixture, or you could go down to this area where everything would be a liquid, okay? So what we need to determine is where is going to be state 2. So in state 2, do we have two properties? Do we know two things? Yeah, so that's a good thing, no? Okay, so for state 2, let's see what I have. So state 2, we know that P2 equals 4 bars, and that T2 equal to 30 degrees Celsius. Okay, so here guys, pay attention because this is now the important part. So this is the line of T equal minus 5.56. So this means that now we're going to have another line here, all right, that will correspond to the T2 equal to 30 degrees Celsius. Yeah, this line of constant temperature when you do the PV diagrams. When you do the TV diagrams, it's lines of constant pressure. So what does that mean? Where is the only place where this curve is going to intersect this line? It's going to be right here, no? So what does that imply? So that implies that, so from the figure, from this data, that implies that state 2 will be on the area of superheated vapor or gas. So basically it's vapor or a gas. It's in this area. Okay, so now that we know what it is, we can go to the appropriate table. So for example, if you look here at the tables, they all have a title, property of saturated refrigerant, liquid vapor. So this is the table for generally, this is the table for this is the table really for this area here, really is for this area here, but also used for this area over here. But that doesn't help to find the properties on this side, no? So what is the table we need to use on that side? On that side, we need to go to the table of superheated refrigerant R22, where everything is vapor or gas. So you see that that figure is going to tell you to which table you need to go. All right. So now we are in table A9, and what do we know from the problem? We know that the pressure is 4 bars. So let's look at 4 bars over here. Okay, 1.5, 4 bars. Here we are. Now, we know case we are not dealing with this line. Our temperature is 30 degrees. All right. So I'll go to the line of 30 degrees. Is this table? Where is the V values? V values in the first column. So what will be the value of V2 will be 0.06872. So if you want, I'm going to just now go down to this page over here, to this document. I'm going to say from table A9, at P equal 4 bars and T equals 30 degrees, we find that V2 is 0.06872. Okay? Let me go back here. I need to go to another page. So now we go from table A9 at, you always need to know two things. So you know P2 equals 4 bars, T2 equals 30 degrees Celsius, we find that V2 is equal to 0.0687 cubic meters per kilogram. Okay, so this one, we're not going to need this one anymore. I don't think so. All right. Okay, so if you remember the problem, this is the problem we are dealing with. So what type of problem is this one? This is constant pressure, okay? So for constant pressure, we need to find what is the work done by the pressure. So if you remember the expression for work done by pressure, was given by the expression integral of P dV, okay? So, I mean, if you want to do it here, you know that specific volume is volume over mass. So this is going to tell you that volume is mass times specific volume. So really you can rewrite the expression above is work equal to integral of P m dV, specific volume, which will give you that the work per unit mass is just equal to the integral of P, but this time instead of being the volume, it's times the specific volume. Because in this problem, what we need to find is what is the work per unit mass, okay? And that is what happens in most cases. 90% of the cases, if not 99, they always ask you to find per unit mass. So if this is a constant pressure process, what does that mean? This would be equal to P V2 minus V1. Okay? So this is, so we can write now, numerical application if you want. We're gonna have work over M is equal to 4 bars, but 1 bar is, you can look at the table, but by now you should start getting familiar, is 100 kilopascals. Okay? 1 equal P2, because of the figure, pressure is constant and is equal to 4 bars, no? So we could say that this will be 400 kilopascals times V2, which we say was equal to 0.06872 minus V1 that we found to be equal to 0.0581. All right, and this should be cubic meters per kilogram. All right. So please go and check the calculations, but for once I have the result with me. This should give you that this is about 4.25 kilojoules per kilogram. Jenny, I like to let you do the calculations, but being on video, I think might be boring for the people waiting for you to do the calculation, okay? But Jenny, I like you to do it. All right, so we found the first question here. The first thing we needed to find in the problem, what is the work done by the piston, okay? So if this is positive, what does that mean? What was the sign? Remember, the sign convention is work positive is work done by the system, no? Yeah? Okay? So this is work done by the piston. All right, now the next thing we need to do is to find what is the heat per unit mass that is involved when this creates the work, or how much heat you need to apply to this in order to have this amount of work done. All right, so in order to do that, what is the equation we're going to use? We're going to use the first principle, which is called on your book the first law, but the first principle of thermodynamics. Which is what? Heat minus work equal to change in energy. But if we neglect kinetic and potential energy, we are just left with Q minus work equal to the change in internal energy. Or per unit mass, we could just say this is Q over M minus work over M equal to D. So this is uppercase U. Remember, for specific values, they always use lowercase. Same thing for volume. You see lowercase v means specific volume, capital V means volume, okay? So same thing with the other properties. For example, this is internal energy, capital U will be the normal energy, lowercase u will be the specific. So where U, if you want here, is just capital U divided by M. All right, so this will give us the equation that the amount of heat per unit mass that is either added or removed needs to be equal to what? U2 minus U1, the change in internal energy, plus the work done by the piston. Okay, so work over M, we already know it is 4.25. Now, in order to find U1 and U2, obviously, I didn't do it before, but we can find them from the tables, no? Okay, so what do we know about this one here? The same thing that we had as state 1, we know is saturated vapor, and we look for V sub G. We can go and look for U sub G in order to find U1, okay? So let's say that would be from table A8. So table A8 at P equal 4 bars, and we know the state is saturated vapor. We can say that U1 will be equal to U sub G. And that U sub G, when we go to the tables, is, so table A8, we look here at U sub G, internal energy, U sub F. Where is U sub F? U sub F would be located, oops, U sub 8, U sub F would be located right here, no? Yeah? This would be the U sub G here. This is U sub F, saturated liquid, or the part F for fluid, right? And G here for gas. But we look at the gas. So that value in that table is at 4. U sub G is 224. Oh, that's 4. Sorry, the one above. Be careful, okay? Sometimes helps to you bring a ruler if you print them. So it's 224 224.24. All right. So I'll go here is 224.24, and the unit for this should be kilojoules per kilogram. All right. Now we do the same thing for you as state 2. We know is saturated vapor, so we need to go to table A9. Is the same as before. This time have P equal 4 bars. And what is the other thing we know is the temperature. But you see, you always know two things. You need to know two things in order to go to the tables. If you only know one, there is no way. Okay? You need to know two things. So here you will find that U2 will be equal to what? So let's see. We go to table A9 at 4. We know that internal energy will be the second column over here. So at 30 degrees, we have the value 245.73. Okay? So I'll come over here, 245.73 kilojoules per kilogram. So now I can go back to this equation here that we just had before. So we can say substituting into Q sub M equal U2 minus U1 plus work over M. All right, so this will give you what? U2 we found to be equal to 245.73 minus U1 we found to be equal to 224.24. Units are kilojoules per kilogram plus work over M that we just calculated to be equal to 4.25 kilojoules per kilogram. Okay, so this gives us that the amount of heat Q sub M is 25.74. If you want to check, it's not that clear on my notes, but not that concerned about the value, kilojoules per kilogram. So again, what does that mean for the system? For the sign convention we're using, this is the amount of heat that you need to add to the system. You need to heat up the system if you want, you need to heat it. If you heat it with this amount of energy, you're going to create 4.25 kilojoules of energy. All right? Okay, so now the reason why I'm doing this problem is probably not from the book, probably came up with it, is because we did study something last time, is that, so this is really the end. I'm just going to put here check. All right, check. You remember what is the definition of the enthalpy? I told you the enthalpy is equal to the internal energy plus work done by the pressure. Okay? Enthalpy, internal energy plus work done by the pressure at constant pressure. All right? So what is really this equation here? When you look at this equation, what is this? Internal energy and this was the expression of the work done at constant pressure. Okay, so really the expression here that we had, Q over M equal U2 minus U1 plus work over M is the same as the enthalpy. So this should be equal to H2 minus H1. Okay, and again, these values for the enthalpy, you can also find them on the table. So here, in order not to go to the another page, I'm just going to do it here a bit smaller. So let's say from table A8, you will find that H1 equal to Hg. And if you go to the tables, what would that be? So let me go to the tables. You see, you also have the values for H, no? This is table A9. So this is temperature, specific volume, specific internal energy, specific enthalpy, and this will be specific entropy. All right. We're on table A8, which is the previous one, at P equal, so you can get it, yeah, P equal 4. What would be Hg? Hg will be equal to 247.48. You see over here? Okay. So 247.48. Guys, please bring the tables to class. I guarantee you that, I mean, you have the video, so you can do it at home, but as in, if you don't practice to go and look on the tables, you're gonna get lost, or the day of the exam is gonna take you forever. Okay? You need to practice. All right, and similarly, you find H2 by looking at table A9. Again, you know two things. You need to look at A9 at P equal 4 and a temperature of 30. So we come here, 4. All right, here we have 4 and 30. H is equal to 273.22. So H2, 273.22. All right. So now if you do the numerical application, you have Q over M will be equal to 2, will be equal to H2 minus H1, which is equal to 273.22 minus 247.48. And this gives you 25.74 kilojoules per kilogram. Okay. Say something, because I'm not sure that actually, I think I talked about it, but I'm not sure we put on the notes, but remember these values. I don't think we talk about this, about the X, no? So what happened when you are in this area over here? So let me just put it on the notes. It will be easier, and then we can come to this one. All right, so basically on either figures of these ones that you have P or TV, you always end up with this kind of curve, where this line here to the left is the saturated liquid or fluid, and this one to the right is the saturated vapor. Okay? So you know that on the left-hand side of this curve, the state of the substance should be liquid. On the right-hand side of this curve should be vapor. And right in the middle is a mixture. Okay? So a mixture means that some of it is going to be gas, some of it is going to be water. So you look at a percentage, let's say if you are right in the middle, you could say that 50% should be liquid, 50% should be gas. If you are a bit more to the left, let's say would be 30% will be gas, 70% will be liquid. But if you get closer to the line here, you might have 80% gas, 20% liquid, no? So you need to have that variable that tells you how much within the mixture is either liquid or gas. So what was decided is that this X, this one will give you what? The percentage of what? Gas within the whole mixture. So this X over here is called the quality factor, but really what does it mean? Is the amount of gas that you have within the mixture, no? Yeah, you look M gas divided by M total. This should be the amount of gas within the mixture. So when you are in this area here, in the mixture, you have a variable X, which is defined as M gas or M vapor equal to M gas plus M fluid or liquid. And the other name of this one, so basically physically means the percentage of gas within the mixture. But it has a name in thermodynamics. They call it the quality factor. Okay? So if you have a substance that is within this area over here, the way to find the value of the property is what? So for example, you need to find the specific volume. You will write down V1 will be equal to V fluid or V liquid plus X, the percentage of V gas minus V fluid. If you do percentage, that's what it means, okay? You can do this will be what? V gas. You do this will be V gas, V liquid, V mixture times X, no? Same thing. So the value of the property. U1 will be this one. If you do the internal energy, you could have U1 will be equal to what? U fluid plus X, Ug minus U fluid, which is the expressions that you have over here. All right, so you can bring this table. You see? Ug minus U fluid. You can do the same thing for the enthalpy, and you'll be able to do the same thing for the entropy later on. So you don't know what is entropy yet. So, and you could do here H1 or whatever would be the number, would be H fluid plus X, H gas minus H fluid. Okay, just to let you know, it doesn't happen in every single textbook and in every single table, but some of the tables, I think table 8.8 had it. You see over here where you have HFG, but they don't have it for U. Okay, the HFG actually what it is UG minus UF, and this would be minus 20.34. So they already do the calculation. UG minus UF, they do it for you. All right, but personally, I don't use it much. I do this column here. Basically, what it means is HG minus HF. No. So what would be this one? Would be 224 minus 20.34 will give you 244.34 plus 36 would be 69, no? Yeah? I don't like to use it, but just to let you know. And I don't know why they have it for enthalpy and they don't have it for internal energy, or they don't have it for entropy. Okay? But just if you had a question, what is this column here? It's just the difference between both of them. All right, so after seeing that, let's do another problem. Now let's do one from your textbook. So this is said. Let's go to another page and let's start a problem. 1, 2, 3, 4, and this time will be the example will come from your textbook. It is number 399. All right, so let's see what 399 is. I'm gonna have it difficult here to go from one page to the other, but I think I should be better off actually opening another file. It doesn't want, okay, so, all right, doesn't matter. So chapter 4, I'll go here to I'll go chapter 4 because I think it would be easier to go backwards. So page down to 399. And at the end of the chapter, they give you all these expressions here, but okay, page down. 399. Oops, what am I doing here? $364. I guess almost there. The bottom. That doesn't look like being the same problem at all. Okay, so might be the 9th edition. Let me close this. We have the 9th edition here. So I think it's on the 9th edition. And this one has no problem. Okay, so I know what's gonna happen. It's problem 399 out of the new edition. So if you have it part of the homework, you already have it worked out for these values, okay? That's probably what happened. It was probably part of the homework. All right, so 399, this would be from the 9th edition. So we cannot, unless I go to the textbook, we're gonna waste time, so let me just give it to you. Okay, it doesn't look that complicated. So basically, this problem is again the same thing. They tell you have a piston cylinder assembly. So you know this is a closed system in which the substance inside is water, H2O. They tell you that neglecting kinetic and potential energy to determine the heat per unit mass knowing that at state 1, the water is at a pressure of 700 psi, and the initial temperature is 550 degrees Fahrenheit. Okay, so then it goes through a polytropic process. That means PV to the K equal constant to a state 2. Where you know that the pressure is equal to 3000. So you need to find the value of the heat per unit mass by 2 methods, which is this type of problems I like, is using the tables, always will be more accurate. Using ideal substance instead of gas, I call it assumption. Okay, so once again, what do we need to do? We need to do the figure. This is the most important part of the problem. No clear figure on the exam, you're not going to get many points, I'll tell you right now, but that's not for the first exam, okay? In this case, here for a change, let's look at TV figure. I put the U because we're going to need internal energies as well. So it's always the same curve, something like this. But this time we go, if this is TV, we're going to go through lines of constant pressure. So the first one is 700. So let me say that we go through a line of constant pressure. That would be this one here. This is the line of constant pressure. All right, so here, now we need to be careful because what is state one? State one, we need to know two things, no? So this is water. We go to the tables. So I'll try to go, let's go to the tables. We are using English units, so this will be English units SI, English units. Properties of water will be table A2, A3, A5, so on, no? So let's look at the pressure. So that should be, I think, table A3E. This one gives you the temperature. Since we mentioned the pressure, let's go to table A3E, 700. So 700 is right here. Is that the pressure? Or is that the, oh, still the temperature, sorry. Table is, this is the pressure, okay? PSI here, pound force per inch square. So we have 700. All right. What is the saturation temperature? 503.23. So if we go here from, so let me write down. So from table A3E at P equals 700. Right now I'm having that T saturation is equal to 503.23. So basically that's what I write over here, no? All right. But what is the temperature? What is T1? So that means that this temperature here, this is T1 here, equal T saturation, is 503.23. All right. So if the temperature is 550, let's say this is T1, what would be state one? State one would be on the superheated or the gas region, vapor region. All right? You see how you need to find the state of the substance, no? Again, this is practice. You need to practice to do it. So here, because T1, if you want T1, this is not T1, sorry. This is saturation. Let me, I don't want to confuse you. T1 is bigger than T saturation, which means that this is going to be on the vapor gas region. Okay? Because T1, 550 is bigger than 503. Okay, so now that we know the state, vapor or gas, we know that actually the table we should be using should be the superheated table. So that should be table A4E, no? So if I go to my page and I write from table A4E, I'm going to go and try to find all the properties. So table A4E. A4E. I need to know two things. So what do we know? We know the pressure is 700, okay, from the top. And we know the temperature is 550. Actually, we could have found the state from table A4E as well. So from table A4E, we're going to find V1 and U1. You can also find H1 if you want, but I'll let you for you to check, okay? So we go to table A4E. What do we find at P equal 700? So 120, hopefully we have 700, and we don't have to interpolate. Okay, 700 here. We look for the first column, second column, and we look at the temperature of 550. So we're lucky to have 550. So what would be, V1 would be 0.728, and U1 would be 1,149. So we find V1 equal to 0.728, U1 equal to 1,149. This would be BTUs LB. And make sure you write down the units, and V will be cubic feet LB. All right, so we know everything at state one. Now we need to know what would be state two, okay? So we need to know two things, but we only know one. So we need to find another one, no? But what do we know about this process? This is a polytropic process. So maybe using that, knowing that, we can find another property here to see what's going on, okay? So, all right, so using the polytropic relation, which is PV to the K equal to constant, we can write down what? P1, V1 to the K should be equal to P2, V2 to the K. We know P1, we know P2, we know V1, no? Okay? We don't really know V1, but what we know the specific volume for V1, okay? So let's just use, or actually you could rewrite this relation because this is equal to a constant, or per unit mass, you can write this relation as PV, P1, V1 to the K is actually equal to P2, V2 to the K, okay? If you can divide by M on both sides and it will cancel out, correct? All right, it's pretty simple. All right, so using this relation, we can find that, let's see, P1, okay, I'll do the algebra, I'm gonna write it. So P1 over P2 will be equal to V2 over V1 to the K, which this will imply that P1 over P2 to the power 1 over K is equal to V2 over V1. Okay? That's per the square root. You put the square root to the other K, you put it to the other side. So at the end, we need to find the other property. We can find that V2 should be equal to what? V1 over P2 to 1 to the K. All right, so we can do the numerical application. This will give you V2. What do we have for V1? V1 we find to be equal to 0.728, if you remember, okay, right here, 0.728. Now P2 over P1, so as P2 is 3,000 divided by 700. Units don't matter because it will cancel out for the piece. To the 1. Oh, I forgot to give you something in this problem. In this problem, they tell you to use K equal to 1.6. So sorry, I forgot to give you that on the problem statement. So you write that now, K divided by 1.6.
Why is it 3,000 over 700? Wouldn't it be 700?
Is 7,000 over 300? Yes, so I guess you're right. So P1, you're absolutely right. I don't know, I was just looking here. This should be 700 divided by 3,000. And if you do this calculation, this gives you that V2 is equal to 0.293 cubic feet LB. All right. So why is this important? Because now we know two things now for state 2. State 2, what do we know? We know P2 is equal to 3,000 and that V2 is equal to 0.293. Okay, so keep in mind this figure over here, okay? We need to keep this one in mind. So we know that P equals 3,000. So let's say the curve to P equals 3,000 should be where? Should be somewhere over here, no? Should be much higher. Okay? So in order to know the state, what can we look at? We can look at, let's say, what would be the value here for the V, no? Yeah, what would be the V value here for the gas? Let's see at this point for this pressure. Okay? So we can either find that from table A3 or table, so let's see, from whatever we want. So let's see, table, I think will be A3E. Let's see, if I'm not mistaken. So we go from table A3E or A4E. A3E I think will be safer. We could also do this for A4E, but let's do A3E where they give us the pressure. So for pressure equal to 3,000, which is right here. Okay, pressure 3,000. What is VG? Is 0.084. Yeah. So table A3E at P equals 3,000, VG equal to 0.084. Okay, so what is V2? We just found V2 to be equal to 0.293, correct? So we know that V2 is higher than this VG. So what does that mean about state 2? Means that state 2 is going to be in this area, no? Correct? So what was V1? Did we find V1? V1 was equal to 0.728. Oh, that was the previous problem. No, it's this problem. The 0.0728, and this one is 0.293. So really, that looks like it's going a little bit backwards, no? It goes from here, let's say, to here. All right? State 2 over here. And it goes through a polytropic process. I'm just going to do a line this way. So this will be your polytropic process, PV to the K equal to a constant. All right, so you see the figure gives you everything. All right, so I'm not sure we're going to be able to finish it, but let me just give you the last steps that we need to do, and we finish it next time. All right, so that means that state 2 is on the vapor gas region. No, that was the conclusion. All right. So what do we need to solve in this problem 4? We need to find what is the change in heat. Okay? So in order to do that, we do as before. Applying first principle thermodynamics. Okay, I'm going to do it. Is heat minus work equal to change in energy, same as before. If we neglect kinetic and potential energy, we get Q minus work equal to du, or per unit mass, Q over M minus work over M equal to lowercase u, lowercase 1. So the same problem as before, so this will give you that Q over M equal to U2 minus U1 plus work over M. Okay, so basically now, I'm going to stop over here, but we do next time. What do we need to do? We need to find first, what is the work done? We need to find this first, no? Which is the work done by pressure. My blue is dying due to the polytropic process, PV to the K equal to C. So we can rederive quickly the expression to give you the work, no? And then from the tables, we find U1. We're also going to have to find U2, okay? So I think we're running out of time, so we finish this problem next time. So guys, you see that you really need to start bringing the tables in order to practice, no? And do these figures. It's not complicated, but if you don't practice, you're not going to get it, all right? When I'm the one doing it, it looks easy. But when you have to do it, If you don't have the practice, it's not that easy, okay? Remember, I'm good at it, not because I'm smarter than anyone, it's because I get a lot of practice. Okay, I practice a lot, no, when you teach a class. So guys, go and practice, okay? I'm gonna stop the recording.